Hi, in this chapter, we will cover magnetic flux and Faraday's law of induction. Let's get started with section 1, okay, induced electromotive force. So we are going to use this word induced or induction a lot in this lecture. So if you don't know the meaning of the word, you better look up now. It basically means created or caused. So, and if you remember from the earlier lectures, electromotive force is basically, we showed it with epsilon, and it meant the voltage. Okay, so let's start with this question. Can we create electricity? So can we create electric current with some wire and a magnet? The answer is yes. So let's see this video first. Let's say you don't have a battery and you need some electricity. The question is, all you have is a magnet like this and some coil, some wire. Okay, so watch what happens again when the magnet goes into the wire. As you can see, as the magnet moves, you see some current here. This is an ammeter. It basically measures the current. So when the magnet goes in, we read some current, but as the magnet is stationary inside, the current is zero. Let's see what happens when the magnet goes out. Now look at the ammeter. As the magnet goes out, we read some negative current. So you can see from this demo that the current is produced when the magnet moves with respect to the coil. Okay, so we can produce electricity with a magnet and a wire. So all you need is a magnet and a wire. Okay, all we need to do is to move the magnet or the wire. So you can have the magnet go to the right. So here it's moving to the right, or it can move to the left. So what you need is basically just the magnet moving to the right or left. And in that case, you will read either positive or negative current. The other option is, of course, keeping the magnet stationary and moving the coil back and forth. That's also possible. And we also saw in the video that if the magnet or and the coil, if they do not move respectively, uh, then there was no electric current. So if there's no movement, then there's no electric current in the coil, even though there's still magnetic fields passing through the wire loops. So the bottom line is, if you want to get electric current, you have to move the magnetic field, you have to move the magnets with respect to the coil. Okay, so we will see that the amount of created electricity, we can talk about electric current or electric voltage, it is related to the change in magnetic flux. Okay, so flux, you can think of it as a flow of magnetic fields. Okay, we have talked about electric flux, if you remember in the previous lectures. So magnetic flux, the idea is the same. So here, instead of electric fields, now we put magnetic field. So the definition of the magnetic flux is basically magnetic field strength, the area. So in this case, we have a wire loop here. So it's going to be the area of that loop. And cosine of the angle between the magnetic field lines, here they are to the right, and the normal vector of the surface. So here, if you have the surface, now the normal vector or the surface vector, I can also show it with A, it's going to be to the right. So if you look at this picture, the surface vector and the magnetic fields, the angle between them is 0. So here you would get BA cosine 0, which is, so this is 1. So you would get BA. This is the maximum flux. What about this situation? Here, the surface vector is in the upwards direction. Okay. And the magnetic fields lines are to the right. So the angle between these two is 90 degrees and cosine 90 is 0, so there's really no flux here. And you can see it from the picture, the magnetic field lines are not really going through the loop. And this is in between, so there's some angle. So for this, in this case, you would use whatever angle you have here in the formula. And in SI units, the unit of flux is Tesla times meter squared, and you can see it from here. Magnetic field unit is Tesla, unit of area is meter squared, so Tesla times meter squared, or you can use Weber instead of Tesla times meter squared. Okay, let's look at this question. So if you remember from the previous slides, what we need is changing magnetic flux, okay? If it changes, then electricity is produced. So let's look at these three rings, okay? So there is a background magnetic field. It's out of the page. So it's coming from the page towards you, out of the page. So the question is, in which loops or the rings, the magnetic flux, B times A times cosine theta, changes with time. This is important because change with time produces electricity. Okay, so now if you look at the first one, what happens is that the first one is only, it basically rocks right and left. Okay, it's like a pendulum. Okay, is the flux here changes, the flux in the middle. So the area is the same, the area of the ring is the same, the background magnetic field is the same, and the angle between the area and the magnetic field is, it's also not changing, right? So cosine theta would be the same. In fact, here, it will be cosine 0, which will be just 1. So here the flux is the same, even though this is rocking left or right. Okay, what about the second one? Now the second one is actually rotating around this axis here shown. Okay, so the area is the same, magnetic field, background magnetic field, it's also the same, but here what changes is the angle between them because this is rotating around this axis, right? So right now the flux is maximum, but when it rotates 90 degrees, the flux will be minimum. So here the flux is actually changing, right? So the flux is changing with time. What about the third? Well, this is basically, there's a spring, this goes up and down. That's the motion here. Again, here area doesn't change, B doesn't change. And the angle between A and B, which is the theta, it also doesn't change. So here the angle is the same. So the answer is only 2. So only in this case, the flux is changing. Okay, so let's continue with magnetic flux. So a bar magnet's magnetic field is not homogeneous, right? So if you have a bar magnet like this, the magnetic field lines are coming out like this. And if you remember, if you're close to the bar magnet, of course, the magnetic field lines are stronger. And if you are away from the magnet, the magnetic field lines are weaker, okay? Weaker, stronger. So if you look at the magnet, the stronger magnetic field is actually shown with denser field lines. If you see dense lines, that means stronger magnetic field. Okay, so what happens as this magnet moves to the right? Okay, as the magnet moves to the right, the strength of B within the loop increases, right? So initially, the magnetic fields inside the loop, they were weak, but now the magnet is getting closer and closer to the loop. So inside the loop, the magnetic field strength is actually increasing. Okay, therefore the magnetic flux through the loop increases. Why is it increasing? Well, the angle doesn't change, angle is constant, area is constant, but the magnetic field strength is changing. It's actually increasing here. So the flux is increasing if this bar magnet is moving to the right. Okay, in this figure, now let's look at this figure. So what you have here is you have one loop, loop one, it's connected to a battery. So if you have a battery like connected like this, so there's going to be a current this direction, so it's going to come out up here, down here, okay? So when you have a current in the loop that we learned in the previous lectures, that you have a magnetic field, right? If you remember the second right-hand rule, which is this one. Now let's hold the wire loop one. Let's maybe this direction at this point. So if you wrap, so if you uh, point the direction of the current with your thumb, and if you wrap this wire, this part, so your fingers inside, they're going to show this direction, right? So so this current will create magnetic fields in that direction. Of course, that magnetic field is also extending here, here, okay? So if you move this loop or this one back and forth, what happens is moving that loop back and forth, we can change the flux on the loop too. So now the magnetic field strength will be changing here, okay, inside loop 2, and that would create electric current on loop 2. And if you connect the ammeter, you can actually measure some electric current here. But if there's no relative motion, so if these are just stationary like this, yes, there's going to be magnetic field, but that magnetic field will not change the flux here. The flux will be constant, so in that case, there will be no current. So you need change of flux, not just magnetic flux, to get some current. Okay, let's look at this question. So you have a wire here, okay? And you have the bar magnet like this. So in order to increase the magnetic flux, so you want to increase the magnetic flux through the loop, what would you have to do? Push it up, push it down, or move the loop? Which one do you think is the correct answer here? Okay, let's see the answer. So the answer is A and B. If you move the bar magnet up, so what's going to happen is, now there is already some flux here, but this part of the magnetic fields lines are stronger than this part because this part has denser field lines, right? So this is getting closer, the stronger part is getting closer and closer to the loop. So if I push the magnet upward, then the flux would increase. So this is correct. Move the loop downward, that's going to be the same thing. If you hold the bar magnet and move the loop down, then it's basically the same effect. Okay. If you move the loop upward, well, the loop would come here, the wire, but here, if you look at the field lines, they are less dense. So the magnetic field, the strength here is less. So the flux would go down, so this is not correct. So the correct answer is A and B. So do we have anything that works on this principle? Yes. So if you have seen one of these induction flashlights, they actually don't have any battery inside. Okay, what they have is there is a coil like this, and there is a magnet like this. Okay, so what happens is you shake it, and when you shake it, this magnet goes left and right. So it basically induces some current, and that current is connected to this capacitor, and the capacitor gets charged. Then at some point, at a later point in time, you can use this flashlight. So it's basically you just charge it by shaking it. Okay, now let's talk about Faraday's law. So we talked about that the changing flux would create some current or voltage. But let's learn what is the formula, like how much voltage or electromotive force a changing flux, changing magnetic flux would create. Now, Faraday tells us that an electromotive force, this basically means voltage, okay, is produced when the magnetic flux through the loop changes with time. Okay, we learned about this. Now, what is the formula? Before that, let's say this, but if magnetic flux is constant in time, then there's no voltage will be produced. But what is the formula? Like how much electromotive force am I going to create? Well, it's basically the flux, change in flux divided by change in time. Okay, there is also factor of n here. It basically is the number of loops in the coil. So in this example, for example, if you look at here, there are 1, 2, 3, 4, 5, 6 loops. So basically, this is the number of loops in the coil. Okay, so this is the main formula that we are going to use here. So basically, the voltage created will be the change in flux with respect to time, and you can see actually from the formula this sentence makes sense, because if there's no change, if theta is constant in time, then this factor here will give you 0, so you would create no electromotive force. Okay, let's look at this example. So magnetic flux through a 20 loop wire, so that 20 will be the n value, right? It's going to be this n. So it changes at a rate of 0.7 Tesla meter squared divided by second. So this change, the whole thing is already given here. It's going to be 0.7, okay? And the resistance of the wire, which wire? This wire. The resistance of this wire is given to be 10 ohms. Calculate the current in the wire. So, well, basically, this epsilon is this epsilon. N is 20. There are 20 loops in the wire. And the rate of change is given to be 0.7. And if you calculate the voltage, it's going to be 14 volts. So you move this magnet back and forth, and it creates 14 volts in this wire. Look at this wire. There's really, like in this setup, there's no battery, there's no voltage source. The only thing that creates the voltage is basically this coil and this moving magnet, which changes the magnetic flux through the coil. If you want to find the current in the wire, well, you would use Ohm's law. Okay, now we know the voltage, we know the resistance, so you can easily calculate the current, which will be 1.4 amperes. So if you think about a microphone is actually, it's based on this principle, the Faraday's induction law. So you have a diaphragm in the microphone, okay, and on that diaphragm there is a coil, okay. So when you speak or when there is some sound coming in, it basically moves the diaphragm right and left, okay, moves the diaphragm, it shakes the diaphragm. Now there's a stationary bar magnet. So in this case, the bar magnet is not moving, it's stationary here, but the coil itself moves to the right and left. So it's constantly moving with respect to the incoming sound. So now we know that because as this moves, the flux will change inside the magnetic flux because it's getting closer and far away from the bar magnet. So that would create some current. Of course, that current maybe will be small, not enough. So you would feed it to. So let me write here current. So that movement of the coil would create a current, and you would feed that current to an amplifier. And after that point, you can actually record the sound. So the bottom line is you need change of flux. You can do it by moving the coil, or you can do it by moving the magnet. Either way. Okay, so now we move to Lenz law, chapter 23, section 4. Now let's remind ourselves that the Faraday's law it says changing magnetic flux creates electromotive force. And Faraday also taught us that the formula was this. If you want to calculate the electromotive force, basically it's going to be N times the change in flux. But what is the direction of the current? Is it going to be clockwise or counterclockwise? So if I have a bar magnet moving to the right, and if I have a coil like this, is it going to be, the current will be here up or down? Now, Lenz's law, it gives us the direction of that current. So this is the second law. It doesn't give us a formula, but it just gives us the direction of the current. So if the external magnetic field, like from a bar magnet, increasing, okay, the external field is increasing, so here the flux is increasing, so inside the loop, the strength of the magnetic field increases as this moves to the right, okay. The flux through the loop in a direction, so the induced current on the loop will be in the direction such that it creates magnetic fields that decreases. So for an increasing magnetic field from the bar magnet, the coil produces some current in a way that it wants to decrease that magnetic field. Okay, what about if the flux from the bar magnet decreasing, then the coil tries to increase the flux. So it's basically, now I'm going to show you the examples, you will get it better, but basically the coil is trying to oppose whatever the bar magnet is doing. So this is the summary of it. So let's see some examples. Before the examples, let's see what happens in steps. So first of all, there is this magnet, bar magnet. Okay, it's moving to the right. So right moving magnets, magnetic field creates flux of increasing magnetic field towards right. So here the flux is here the magnetic field is weaker, here stronger. As this moves to the right, what happens? The magnetic field strength inside the loop, it increases because this is getting, so this part, the stronger part, is getting closer and closer to the loop. Okay, in the second step, the magnetic field through the loop is towards right and its magnitude is increasing, as I just said. Okay, the third part is now the Faraday's law. Changing flux, it creates electromotive force. And because this wire has some resistance, so you can calculate the current by dividing the electromotive force or the voltage, induced voltage, by dividing it by the resistance of the wire. Okay, so the magnetic field to the right is increasing. Why is it increasing? Because it's getting stronger because this bar magnet is moving to the right. So the loop will oppose that by trying to decrease the flux to the right by producing induced magnetic field. So because of this magnet, the magnetic flux, which is where the magnetic fields are to the right, is increasing. What this loop will try to do is to oppose it. So it's going to create magnetic field lines to the left. Okay, it's basically trying to oppose what this magnet is doing. So some induced magnetic field, so some magnetic field will be induced by this loop. So the magnetic field lines here, you see these lines, they are not from this magnet. From this magnet, they are actually to the right, but they are from this loop, and they are to the left to oppose this magnet. So the current needs to create magnetic field lines as shown. So the Lenz's law tells us there's going to be magnetic field lines, induced magnetic field lines in this way. So induced magnetic field lines to the left inside the loop, they are to the left. So to be able to induce such a magnetic field, now use the second right-hand rule here. Now so to be able to create inside magnetic field to the left, what happens is you have to have a current in this direction. as shown here. So this is the induced current. And you can check it. Now, point your thumb in that direction. Okay, point your thumb in this direction and wrap the wire. Okay, wrap the wire here. And you're going to see that inside your fingers will point, they will curl inside the loop to the left. So that's going to be the magnetic field induced. Okay, so induced magnetic field to the left can only be created if the induced current I, which is this one, is in the direction as shown here, which I just mentioned. So again, we use second right angle for that to find the direction. Again, it's basically the Lenz law, which tells us the direction. Okay, and these induced magnetic field lines, see, these are the induced magnetic field lines. They are as if they are created by a fictitious bar magnet positions as shown. So if you look at these magnetic field lines, they are like as if there is a bar magnet here. Fictitious means not real, okay? There's no bar magnet here, but if you look at these magnetic field lines to the left, it's almost like this loop creates its own bar magnet. It's not real, but the effect is the same as. So the North Pole will be here because the magnetic field lines are to the left inside the loop. So this is basically how it works. The electricity induction, the current induction in a loop of wire with bar magnet. Okay, so there are actually four possibilities um, for setup. So one of them is we just did this actually. So you can have a bar magnet whose north pole is on the right and it's moving to the right. Okay, so basically the magnetic field lines inside the loop are to the right, and so the loop will try to oppose by creating its own magnetic field. Okay, so because the flux is increasing to the right, okay, the flux is increasing and B is towards right. So the loop will try to create its own induced magnetic field. Let's call it induced. Okay, and it's going to be to the left to oppose this incoming magnet, right? So to be able to get induced magnetic fields from the loop to the right, now use your second hand. So this is the second hand rule. So to be able to create magnetic field lines inside the loop in the leftward direction, you have to have so imagine your fingers inside the loop are curling towards left. So there is only one option where the current is in this direction. So if you look at here, the induced magnetic field lines are to the left, right? So these are the magnetic field lines that are created by this current. Now, if you think about it as in terms of a fictitious bar magnet, so this would correspond to a bar magnet like this. So to create magnetic field lines to the left, you would have a bar magnet like this whose north pole is on the left. Okay, what about this situation here? So now, again, this is moving to the right, but here, again, the flux is increasing, right? Because as this moves to the right, here it's stronger. So the flux inside the loop gets stronger and stronger. Okay, the flux is increasing. But here, in this case, the magnetic field lines are towards left. You can see that they are to the left. So increasing flux, magnetic field lines are to the left. So this loop now is going to try to produce magnetic, so there's going to be induced magnetic field lines now to the right, because here the magnet has magnetic field lines to the left and it's increasing. So basically this loop will try to create magnetic field lines to the right. So that's going to be induced magnetic field lines direction. So now use the second right-hand rule to be able to find which direction should be the current, which should be the direction of the current on the wire, so that it creates magnetic field lines, induced magnetic field lines to the right. And you can easily find out that it should be the direction of the current should be this way. And in terms of fictitious bar magnet, it will even though there's no such bar magnet like here, but if you try to push if you make this bar magnet, if you push it to the right, it will actually push you back. The wire, by creating a current and the induced magnetic field, it will actually push you back a little bit. And you can see it from here, south and south. So basically the wire is opposing to the magnet. The same thing here in the first example, north and north. Okay, let's look at the third example. Now the third situation is now because the bar magnet now is moving to the left, so the flux here is decreasing, right? Because as you go away from the loop, now the inside the loop, the magnetic field strength will be less and less. Now, what is the direction of the magnetic field lines? They are to the right. The flux is decreasing, magnetic field is to the right. Now, the loop is going to try to oppose again what the bar magnet is doing. So it will try to increase the flux where the magnetic field lines are to the right. So it will try to induce magnetic field to the right, because magnetic field lines to the right and the flux is decreasing. So this will try to increase the flux. Again, use the second right-hand rule, and you will find again the current should be in this direction. And in terms of fictitious bar magnet, it will look like this, because magnetic field lines to the right, you can only create them with a bar magnet like this, right? So what's happening is this, so you are actually pulling the bar magnet away from the loop, but the loop itself now is trying to oppose you as always, and now trying to pull the bar magnet back to itself. You can see that this is north, this is south. So it's always like opposing to the whatever this bar magnet is doing. Now finally, in this case, this is again moving to the left, the bar magnet, and we have the south pole, so the magnetic field lines are to the right. Okay, so the flux is decreasing because this is moving away from it, and the magnetic field lines are towards left. So this loop will try to create some, there's going to be some induced magnetic field. It will try to create magnetic field because the flux is decreasing. So it will try to increase the flux, and again, use the right-hand rule, second right-hand rule, and you will find the current should be in the up direction. So this is the four possibilities of the Lenz's law. Okay, here's a question. You can pause here and think about the solution, try to solve it. The question is basically, what is the direction of the induced current if the magnetic field suddenly increases? So this loop is not moving anywhere, but the magnetic field increases. So what should be the current direction? Maybe there's no current induced. If there's current induced, is it going to be clockwise or counterclockwise? So this is clockwise. So let me draw here. This is clockwise, and this is counterclockwise. Okay, if so the magnetic field lines are into the page, okay, and they are increasing. So the flux is increasing, magnetic field lines are into the page. So the loop will try to oppose it by Lenz's law. So it will try to create magnetic field out of the page. So inside it will induce magnetic field out of the page. Okay. So to be able to get magnetic field lines like this, induce magnetic field lines out of the page, you have to have, let's see, let's imagine that you are here. So you're going to grab this part of the wire. Okay. So use your second right hand rule. So if you want your fingers to curl out of the page here, your thumb should be in the up direction. So what you find here is the current should be counterclockwise. The induced current should be counterclockwise. Okay, let's look at this problem now. So a wire loop is being pulled away from a current carrying wire. Okay, so now definitely, so if there's a current on this wire, it's going to create some magnetic field lines, right? So it's going to create magnetic field lines everywhere. And now you have the loop here, the wire, and you are pulling it to the right. The question is, what is the direction of the induced current in the loop? Think about it. First, find the magnetic field direction here, the magnetic field that's created by this wire. And then you can think what direction should be the current so that this wire, the loop, is so that it can oppose the change in flux. Okay, the answer is clockwise. So the reason is, first of all, let's find the magnetic field direction. So to find the magnetic field direction that this wire creates, you can use the second right hand rule. So the current is in the up direction, so your thumb would show would be directed in the upward direction, and grab this wire. So basically curl your fingers around this wire, and here your fingers would actually go into the page, right? So on the right of this wire, the current will be into the page. Okay, and there's one more thing. The current, if you remember from the earlier lectures, the magnetic field that this wire creates, it actually decreases with R. Okay, now as this loop moves to the right, while the area is not changing, the angle is not changing, but the magnetic field lines inside, the strength of the magnetic field, it decreases because the magnetic field created by this wire, it decreases as 1 over R. So now the flux is decreasing now, and the magnetic field is into the page. Okay, so this wire, it's going to create magnetic field into the page again so that it could compensate the decreasing flux. So it will try to increase the flux with magnetic field into the page. So to be able to get magnetic field lines, induce magnetic field lines inside here into the page, use the second right hand rule here, and you will find the current should be clockwise here. Okay, another question. Now, a wire loop is being pulled through a uniform magnetic field. Okay, the magnetic field is into the page, it's uniform. The question is, what is the direction of the induced current? Now think about it. Okay, the answer is there's not going to be any current induced. The reason is, if you remember the formula for the flux, magnetic flux, the magnetic field is not changing, area is not changing, and the angle is not changing. So if flux is constant, yes, there is some flux, but it's not really changing, then there is not going to be any induced current in this case. Okay, now another question. So here, a wire loop is being pulled through a uniform magnetic field that suddenly ends. What is the direction of the induced current? So now if you look at it here, there is magnetic field lines here. Okay, magnetic field region is basically here. And it ends here, okay? So you're pulling it to the right. Now, if the flux is changing, then yes, there will be some current, and you have to find the direction of that current. So think about it. Okay, so let me explain it. So as this moves to the right, so now there is some flux, there is some magnetic field, and the area is actually this area. So if you want to calculate the flux, you would actually not take the whole area, but only this area. So magnetic field strength B times this area. Now as this moves here, maybe it's going to come like its position will be something like this as it moves. Now the area goes down, right? So the flux is decreasing. Okay, what happens if the flux is decreasing? Now this loop will try to oppose it. So the magnetic field lines are into the page. So the loop will try to produce some magnetic field lines to increase the flux into the page. Okay, to be able to produce magnetic field lines into the page, what you need is a clockwise current. Okay, let's continue with Lenz's law. There are a couple more things that I want to tell you. There are interesting examples. For example, magnet falling through closed loop. So let's say we have a loop like this. This is a wire, and the magnet is actually falling through it. So what happens? So here, changing flux as the magnet, of course. So there are some magnetic field lines. They are in the up direction because this is the South Pole. Magnetic field lines go into the South Pole. They go out of the North Pole. Okay, so as this falls down, of course, it's getting closer and closer to the loop. So here, the changing flux through the loop will cause induced current in the loop. Okay, then the induced current will create induced magnetic field lines opposing the bar magnet. Okay, let's look at here. So this is falling down, and because the flux is increasing and the magnetic field lines are up, so the loop will try to oppose it. So it will try to produce magnetic field lines down so that the flux goes down. Because if there's magnetic field lines in the up direction, if the loop creates magnetic field in the downward direction, then they basically cancel each other to a degree, not completely. Okay, so by that way, the flux would be reduced. Okay, so to be able to create downward magnetic field lines, you have to have the current in this direction here. So this is the direction of the induced current shown in green. Okay, so basically the induced magnetic field lines are in the downward direction. So you can think of this, there is a fictitious bar magnet here with the South Pole at the top. So that way you would have magnetic field lines this way. So now look at this bar magnet. So it's falling down. If you hold up another magnet like this with the South Pole in the up direction, it will basically repel each other, right? So you would actually slow down this falling bar magnet. So it's almost like friction, right? Slowing down. Again, there's really no fictitious bar magnet here. It's just you can think of it as as if there is a bar magnet by just looking at this induced magnetic field lines. But what actually stops this, and not necessarily stop, but slows down the bar magnet, is actually the induced current and the induced magnetic field lines on the loop. So as a result, the magnet will drop. It will continue dropping, but it would feel some magnetic braking as if there is friction. Okay, what happens if I make the same experiment but with a broken line, the broken wire? Now this time no induced current will be generated because the loop is broken. If the loop is broken, if the circuit is broken, you cannot have currents, right? So you have to have a closed circuit. So no opposing induced magnetic field lines will be created. If you cannot create current, then you cannot create opposing magnetic field lines. Okay, so there's not going to be any induced magnetic fields here if the wire is broken. So the magnet, it will drop freely without any resistance. Okay, what about this example? Again, we are talking about Lenz's law. Now we have the loop here. Now in this example, what changes is the magnitude of the magnetic field lines. Now you can see that they are dense here, but they are less dense here, right? So the magnetic field lines are to the left, okay? What happens is they are just getting less denser. So the flux is then through the loop is decreasing. Magnetic field is to the left, the flux is decreasing. Now, again, the loop will try to oppose this situation, okay? So to oppose the decreasing flux, where the magnetic field lines are to the left, it will induce magnetic field lines to the left so that the flux increases, okay? So these lines that I'm gonna draw in red right now, like this, these are actually the induced magnetic field lines on the wire to increase the flux so that the loop actually, by the Lenz's law, so that it can oppose the change in flux. Okay, now we know the direction of the magnetic field lines, induced ones. Okay, they are going to be to the left. So what should be the direction now so that I can get induced magnetic field lines to the left? Well, if you use the second right-hand rule, you will find that if you look at here, for example, now imagine, so you don't know the direction of the current now, okay? So imagine you hold this part so that your thumb points down. So in this case, your fingers inside would curl to the right. So that wouldn't work because we want the induced magnetic field lines to the right. So here then it means you have to hold this part of the wire so that your thumb points up. Then you can verify that actually your fingers would curl this wire inside so that inside they will be to the left. So from here you find the current should be in this direction. Okay, what about the falling ring? Now you have some background magnetic field, but it's restricted to this area. So only in this area there is magnetic field. Okay. So now as this ring moves down, let's say it moves here. Let me try it again. Let's say the ring fell here. So let's see what changed. Well, the area is the same, the angle is the same, and the magnetic field strength is the same. Okay, so nothing changed. Well, there is flux, but flux did not change. So then there is going to be really no current. But right here, if you look at here, the area with the magnetic field line, the area with the magnetic field, it's getting less and less. So the flux is changing here as this ring starts to get out from the magnetic field lines, this magnetic field region. So there is going to be induced current at this position. And as it gets out completely, so after the ring is here, after this point, it will continue falling, but there is not going to be any current on the ring because, well, basically there's even no magnetic field here, so there's not going to be, we cannot really talk about change of flux. There's even no flux here. So the current is induced only when this ring is actually leaving the magnetic field region. And this is where the flux changes. Now let's think about the direction of the induced current. Now here, look at it. So as it falls down, this area with the magnetic field, now if you want to calculate flux again, you don't take the whole area, you take the area with the magnetic field. So this area is getting smaller and smaller as the ring falls down, right? So the magnetic field lines are out of the page and the flux is decreasing. Now this ring will oppose the situation by trying to increase the flux in the out of the page direction, okay? To be able to increase the flux, there should be a current. Again, use your second right-hand rule. The current should be in this direction. Okay, what about the forces on this ring? Now, this goes back to the previous chapter 22. So now we know that there is, now look at this figure now, we know that there is some current in this direction, right? This is the induced current. Okay. Now the ring has induced current I, and the upper part of the ring is in the magnetic field. Remember, if there is current and if there is magnetic field, then there will be some force. How do you find that force? Well, it's going to be current times magnetic field times the distance or the length of that wire. Okay. Now to find the direction of the force, magnetic force, this one here, remember you have to use the first right hand rule. So this is the rule where you're basically the direction. So let's look at here. So let me erase this. So the direction of the current here is in this direction to the left. Okay, so your index finger will show to the left. Okay, so the magnetic field lines are out of the page. Okay, so so your middle finger will point towards you, and your thumb will give you the direction of force, which is in the up direction here. Again, you see some magnetic braking here, so the ring is falling down, but there is definitely mg. It's falling down with the effect of mg, but there is some magnetic force in the upward direction, so it kind of reduces the acceleration a little bit. And you don't have to have always rings. You can have a sheet of metal like this. This is not a ring, this is a sheet of metal. Okay, and it can fall in the background of magnetic field like this. Okay, so there will be some currents induced. Okay, so let me go back. If you have a ring, then you have current induced on the ring, right? Like this. But if you have, let me go forward. If you have a sheet of metal like this, okay, now there will be induced currents at all levels, like small circles, large circles, like this. These are called eddy currents. So, and they can be powerful brakes, and they're used in some devices which employs magnetic braking. One of them is exercise bikes like these. They actually have when you are on the exercise bikes, the hardness that you feel is actually coming from these currents. There's really no touching parts that braking mechanism or that hardness is actually coming from these eddy currents. So here the braking part or so is actually coming from, now this sheet of metal is falling down, okay? And because there's magnetic field lines and because the flux is changing, okay? So if I take this, for example, this part of the metal, now there is magnetic field on this here, but as this falls down, this part of the metal, the flux in this part of the metal will be decreasing. So there will be these eddy currents will be produced. It's just like the ring in the previous slide. And because it's not just like ring, it's everywhere, the sheet of metal, it's extended object, and this continuously happens, okay, as the sheet of metal completely gets out of this magnetic field region. So the sheet of metal feels continuously this force in the up direction. So with the bikes though, you don't have a linear motion, but there is a circular motion. So inside it, there is constantly a rotating, there's magnetic field, there are magnets and a rotating metal that where eddy currents on it are induced, and they create some sort of braking or they create some sort of hardness. Another example to Lenz's law is basically the induction stall. Maybe some of you guys saw these types of stalls. They actually work with magnetic field, so there are coils inside, coils like this, okay? So when you turn it on, the coil is actually producing not heat, but magnetic field. So you can touch it, you can touch with your hand, and it's not going to, you're not going to feel any heat actually. But if you put a metal like this, a pan like this, so what happens is that it actually will create those changing magnetic fields. They would create eddy currents, and because now there are currents in the pan, but the pan also has some resistance, right? And that resistance, it creates some power. It's related to resistance and the current, which is dissipated. That power is dissipated as heat, and the heat cooks the egg. So this is basically, again, using eddy currents and magnetic field to cook food in the kitchen. Now let's move to mechanical work in electrical energy. Okay, so in this example, so we will talk about motional electromotive force. Again, electromotive force is like voltage. How can you produce electricity by let's say, a falling rod? Let's say we have a circuit like this, a wire, it's connected to this rod, and this rod is falling down with the effect of the gravity. Okay, so the conducting bar, it falls due to its weight, mg. As it falls, the magnetic flux decreases in the loop because the area decreases and the current is induced. Why is the flux decreasing? Well, B is the same, angle here it's actually 90 degrees. So the area is decreasing. See, the area with the magnetic field here, now look at, this is our loop. This area is actually decreasing as this bar falls down, okay? So when the flux decreases or increases, well, basically when the flux changes, we get current or voltage. Okay, Lenz's law gives us the direction of the induced current as shown. Now this is going to be the current direction. You can, so how do you find it? Again, we're going to use Lenz's law. So here, the magnetic field lines are out of the page and the flux is decreasing. So the loop will try to oppose it. So it's going to increase the flux. Again, the flux is decreasing because of the decreasing area. So the loop will try to oppose it by increasing the flux with magnetic field out of the page. Okay, so to be able to get increasing flux or induced magnetic field lines inside the loop out of the page, you have to have the current in this direction. use your use the second right-hand rule, and you can find the direction of the current. Okay, now since both current and magnetic field is present, now there will be some magnetic force on the rod, right? So now this time you're going to use here the first right-hand rule. So your index finger is to the right, and the magnetic field is out of the page, which gives you the force in the up direction. Again, this rod will continue falling down, but because there's some force in the up direction, the acceleration will be less than g. So this magnetic force F will decrease the acceleration of the falling bar. It acts like a friction. So if you like, it's like magnetic friction. Okay, so let's think about this situation now. So instead of gravity, let's say someone is pushing the rod to the right, okay, so that the rod moves with constant speed. Let's say this person is pushing it in a way that the rod has always the same speed. Okay, so the flux changes due to the changing loop area. See, initially the loop area is this one, okay, and finally, let's say at this point it becomes like this. So the loop area is increasing, so the flux is increasing. Now the Faraday's law, it tells us the current induced will be change in flux with respect to time. We don't have n here because we only have one loop here, so n is basically 1. And the Lenz's law gives us the direction of the current induced. So let's see. So the magnetic field is out of the page and the flux is increasing. So the loop will try to decrease the flux to oppose it. Okay. So to decrease the flux, because the magnetic field lines are out of the page, so the loop will create magnetic field into the page. So the induced magnetic field lines will be into the page. Now, to be able to create magnetic field lines into the page inside the loop, use the second right-hand rule and you will find that the current should be in this direction. So this is the Lenz's law. Now let's write down the change in flux. So the flux here is B times A, okay? And if I put a change in front of it, just like, so this is Greek letter delta, it means difference or change. And I would put the same thing here. Now B comes out because B is constant, it's not really changing, but the area is changing. Okay, now I can write this area as L times the distance, right? So X times L, so this could be X, okay? And I can write X as V times delta T, right? The change in X, so here L is not changing, so it's gonna come out of the delta actually. So what changes here is delta X, and delta X is actually delta V times T. This is from physics 1. Now V is constant, length is constant, so they come out of the delta, just like here. But time is changing, so we'll leave it like this. So the change in flux, we can write it as B times V velocity of this rod, or speed of the rod, length of the rod, here this is L, times delta T. So this is going to be the flux. Now, the Faraday's law tells us that the induced electromotive force, or the voltage, or the potential, the same thing, it will be the change in flux, right? So if I divide this flux here, which is this one, if I divide it by delta t, what I'm going to get is B times V times L, which is here. So basically, if you have such a setup, and if the rod moves with velocity v, then you would get the voltage, induced voltage, it will be B times V times L. Okay, so let's imagine that the wires that are connected here, this section of the wire is, let's say this is ideal. That means there's no resistance. So whatever voltage is created here, that means it's going to be created on the rod. So the voltage will be created here. So let me write as epsilon, okay, electromotive force. So it's going to be created on the rod. So we learned in the previous lectures that we can actually relate the voltage to the electric field, right? So if there's a voltage difference, then that always means there is electric field. In fact, what moves the electrons in the wire, what creates the electric current, it's actually the electric fields in the wire. Okay, so how can we move to or find electric field strength if we know the voltage at some part of the wire here is on the, basically I'm talking about the rod. So the formula is V equals E times L, okay? And you can find the electric field, basically divide the voltage by the length of the wire. Here it's going to be the length of the rod, okay? So in this case, the electric field, so let's actually move here. So the electromotive force we calculated in the previous slide, it will be B times V times L. Now, if I divide the voltage, so remember this is voltage. So if I divide the voltage by L, the length of the wire, so I'm going to divide it by L. So basically this L will be gone. So it's going to be B times V. So the electric field will be B times V. So if the question is, what is the electric field inside the rod induced? It's related to basically the background electric field times the velocity. Okay, changing flux, it induces electromotive force or current, we learned this, which is actually caused by the induced electric fields. Electric fields move electrons and they create current. So in this chapter, we don't talk about really Maxwell's equations or electromagnetic theory, but when you take that class, maybe in the future, you will learn that changing magnetic fields will create basically electric fields, and this is what's happening here. So those electric fields are actually creating the currents on the wires. Okay, let's move to power. So here we are going to calculate the power that this person provides to the loop. Okay, so in the previous slide, we learned that the electromotive force induced in the circuit or in the loop here would be B times V times L. Okay, so if you want to find the current in the circuit, well, there is some voltage and there is some resistance in the lamp. Okay, so if you want to find the current, now you know the voltage here, you know the resistance. Just use the Ohm's law, and so voltage divided by R would give you the current. So the voltage is this one, BVL, divided by R. This is going to be the current. Okay, so now here, remember from chapter 22 that if there's magnetic field and if there's a current, then there will be some force. Okay, so on this rod, there will be some force because there is current on it, and it's also inside a magnetic field. So what is going to be the amplitude of this? Well, you can first find the direction if you want. So the current is going down, so use the first right hand rule. So your index finger is pointed down and magnetic field is out of the page. And if you use your right hand, so your thumb is showing to the right, so this is going to be the direction of the magnetic force. Now, what is the magnitude? We find it from the formula I times B times L. L is basically the length of the rod, okay? So the current, we just found it here. So this is going to be the current here. And B times L, if you just do the multiplication, the force will be B squared V L squared divided by R. So this is the magnetic force on the rod. Now, this person is pushing the rod, right? So there is the mechanical power provided by the person. So the mechanical power delivered by the external force is, if you want to calculate it, the power is given by the force, external force, times the velocity of that rod. Now, we don't really know what the external force is, but we could actually find it from the information that, if you remember when we started with this problem, I said the rod moves at a constant speed, so there's no acceleration. That means the net force is zero, right? So if the net force is zero, or if there's no acceleration, then that means these two forces they are in the opposite directions, but in magnitude they are equal, right? When the net force is zero, then this thing can go at constant, the rod can slide at constant speed. Okay, so from this information, I can actually find what external force is. Well, external force is equal to magnetic force. And here I already calculated the magnetic force, so it's going to be B squared V L squared divided by R. Okay, now I can calculate, now I can use this equation to find the power that this person is providing to the circuit. Okay, power created by the external force is F times V, while the force will be this one, times V. If you do the multiplication, it's going to be B squared, V squared, L squared, divided by R. Okay, this is the power that this person is providing to the circuit. Now, that power it should be used up by this lamp, right? Let's calculate the power on the lamp and see if they are going to be the same. So the electrical power in the light bulb, you can calculate it by I squared times R. So the current, again, let's find the current here. Use this current. The current in the wire is this one. Take the square and multiply it by R, the resistance of this light bulb. And if you do the multiplication, you actually find the same answer just like here. That makes sense. They're the same. Therefore, mechanical power has been converted directly into electrical power. So this is some sort of a generator that if you, as a person, if you push it, then you can create some electric potential, and you can actually light up the light bulb with that. Okay, let's look at this example. Now, in this example, a conducting rod slides on a conducting track. So basically, this is a conducting rod, just like in the previous example, and there's this wire here. Okay, so the B field directed into the page, it's cross, shown with cross into the page. What is the direction of the induced current? Now take a look at it. Try to understand what happens to the flux, and by using the second right-hand rule, try to find the direction of the current. Okay, so now look at the area. So if we have to think about it in terms of flux. Now look at this area. This, as the rod moves to the right, this area is actually getting larger and larger. So the flux is increasing and the magnetic field lines are into the page. So the loop, the circuit will try to decrease the flux to oppose the situation. Okay, so to decrease the flux, it will create magnetic field lines that are opposite to these ones, which are going to be out of the page. So the magnetic field lines induced will be out of the page. Okay, to be able to get these magnetic field lines, what should be the direction of the current? Well, if you use your right hand by using the second right hand rule, the current direction should be in this way. So it's going to be counterclockwise. Okay, now let's move to generators and motors. Okay, so let's start with generators. Electric generator, it basically converts mechanical input into electrical energy. Okay, what is that mechanical input? Well, it could be water flowing. So in the dams, for example, water flows and electricity is produced. Or it could be the wind blowing towards a wind turbine, or it could be steam energy. So basically, generators are taking the mechanical input and turning it into electrical energy. So the generator is basically something like this. So there is the mechanical input. It basically rotates this mill. It's connected to this circuit. Okay. So it could be maybe there's a fan here. So it could be water flowing in or wind turning this. Okay. So when this turns, this loop, if you look at this loop, the area doesn't change. So the area is the same. Magnetic field strength is the same, right? It's coming from these magnets. But what changes is this theta. This theta is actually changing with time. So theta, I can write it as omega times t. Omega here is the angular speed. So now, if you look at this loop, so basically the flux through this loop is changing as this rotates, right? For example, when the loop is like this, the flux is zero, right? Because it will be the angle between the magnetic field and the area vector will be 90 degrees, and cosine 90 will be zero. But when the flux, sorry, when the loop is maybe like this, then in this case, the flux will be zero. But the bottom line is BA is not changing, but the cosine omega t is changing with time. So that means the flux depends on time. And you know what happens when the flux changes with time? Well, it produces electromotive force or voltage. And the formula, if you remember, it's N. Here, N is 1, but in general, there are many loops. So N times change in flux. Now, here in this formula, I wrote it as differential. So it's basically just take the derivative of cosine omega t with respect to t. So the derivative of cosine is sine omega t, and if you use chain rule, there is an extra factor of omega. So this is the produced EMF, electromotive force. And if you look at it, it actually depends on time. That makes sense. And if you draw it, so let's draw the voltage. Now, so that current is actually, or the voltage, it actually creates voltage between these terminals. Because if you look at it, one of the terminals is connected to this one. The other one doesn't touch this one. It goes through without touching and is connected to this one. So we are actually collecting positive and negative terminals from here. And we can connect it to electric light bulb or anything else. So if you draw this formula here, respect to time, so this is the time, and the y-axis is the voltage, induced voltage on the circuit. Now, if you look at it here, what is the maximum that you can get from this formula? Well, sine can be, maximum value for sine is 1. So the maximum I can get from here is b times a times omega times n. We actually have n here. I forgot it. Okay, so n b a omega. And the minimum from sine that you can get is actually -1. So it could be negative nba omega. So basically, the voltage becomes positive and negative between these maximums and negatives, maximums and maximum value and the minimum value. By the way, when you take the derivative of cosine, you actually also get a negative sign, but I was not interested in the negative because here I'm just interested in the magnitude. Okay, so the produced EMF, electromotive force, is, we learned in the previous slide, BA omega times sine omega t. This should be sine. Okay, this should be sine. So here omega is again the angular speed. In SI units, you would use radians per second. So if you want to do the conversion, if you need to, well, then one revolution. So one revolution means 2 pi degrees rotation, so one full rotation, or 360 degrees, divided by second. So you would convert it to radians as 2 pi radians divided by second. So you can relate the angular speed to the period. So here t is period, and the relation is omega equals 2 pi divided by t. T is period. And what is the meaning of it? Well, it basically answers the question, how long in seconds one full rotation would take? Okay. So for example, if 4 full rotations happens in 1 second, what is the period? Well, if in 1 second 4 full rotations happens, then one full rotation should happen in 1/4 of the second, and that will be 0.25 seconds. So the period would be, in this case, 0.25 seconds. And what about the other definition? It's the frequency. It's also important, and it's defined as the inverse of the period. Okay, F is frequency, and it's defined as it basically answers the question, how many rotations in 1 second? Okay, the period is how long does it take for one full rotation, and the frequency is how many rotations in 1 second. So they are inverse of each other. And the unit of frequency is 1/seconds or hertz. You can also see hertz, Hz, it also means 1/seconds. Same thing. And also we have this relation, omega equals 2 pi divided by period, which is here. And instead of period, you can write 1/frequency, which is here. If you use that, you can write angular speed as also 2 pi frequency. Okay, now let's move to electric motors. So electric motors are the reverse of generators. So generators are producing electrical energy from mechanical input, but electric motor is producing mechanical input from electrical energy. So we provide electrical energy, and the motor provides us with mechanical input. So let's say it could be, so the motor could be connected to a to some setup like this in the car maybe. So this could be the electric motor in a car, and it could be related to other things. So now, how do you make, so basically to produce this mechanical rotation, this wire, this loop should rotate, right? So how do we make it rotate? Well, basically you connect it to a electrical input. You need alternating current, AC. Okay, and also it becomes positive and negative all the time. So now if you give currents here, let's say initially in this direction, so what happens is, now there is current and there is magnetic field from the magnets this way. Now you can use the first right-hand rule, and you will find there is actually a force in this direction. So that force, we actually did this in the previous chapter. That force, if you take this point, the axis of rotation, with respect to this axis of rotation, it will actually create some torque, right? So this is the force, this is the distance, let me call it r. So there's going to be some torque, and it will be related to, so it will basically R times F. So this is the torque from this force, and also this force will create some torque just like this. So torque is basically a rotational force, and ultimately it will rotate this thing. Okay, now we are moving into a new section. It's inductance. As I said in the beginning, we will use this word a lot in this chapter. So to induce inductor, inductance, induce magnetic field, induce current. So you have to learn the meaning of this word. So what we learned in the previous slides, we learned changing current in coil 1 will produce magnetic field. So if you connect the AC voltage source here, so AC means it's not like battery, the battery is DC, direct current. AC is alternating current. So it basically becomes positive and negative all the time, just like the 220 volts on the wall. Okay. So if you have a current changing all the time, what happens is now it will create. So if you connect the DC, it will create magnetic field lines, but they will not change. But if you connect an AC source, then you will create magnetic field lines, and they will also change in time. So they will be to the left, to the right, to the left. So what happens if the magnetic field lines change? Also, that magnetic field lines extend to the other coil. So they extend everywhere. Okay. Now in coil 2, there will be inside, there will be change of magnetic field lines. And we learned that if magnetic field changes, the flux changes. So it creates some voltage. So there will be some voltage induced in coil 2. See, there is really no connection between the coils. There's no wire connecting them. You are getting current or voltage in the second coil by just induction. Okay, this is, you're creating current, you're inducing current in the second coil by magnetic induction, not really with a cable. Okay, so we learned this, right? So coil 1 produces changing magnetic fields, and coil 2 is it's having some induced current and voltage. Okay, now the question is, um, there's also opposite current induced in coil 1. So the current is not only induced coil 2. Now we haven't mentioned, we have mentioned this, but we haven't mentioned that there is also some current induced in the opposite direction to the change of current in coil 1. So there's also opposite current induced in coil 1. So now let's just focus on coil 1. Let's forget about coil 2. So on coil 1, changing I1. So there is some current, it's I1. It's provided by the voltage source. Okay, it's not induced, it's provided. So it will cause changing, when it changes, it will cause changing field, right? If it's going, in this to the left or to the right, it will create magnetic fields to the left and right all the time changing. So that means the flux through coil 1 is also going to be changing. So what happens if the flux is changing? Now, changing flux on coil 1 will induce opposite magnetic fields. You learn that from, that's basically Lenz's law. And so create induced current opposing the change in I1. Remember, I1 is coming from the voltage source. And so it will create changing magnetic fields. But those changing magnetic fields, they will cause changing flux, and that this coil will try to oppose it and create its own magnetic field to oppose it, and to be able to create opposing magnetic fields, it needs to create some current. And this is called self-inductance. Okay, self-inductance is basically the current induced in the wire itself. Okay. Okay. So when current due to the battery passes through a coil, here we have a battery, there is a resistance, and there's a resistor, and there is this coil connected to the circuit. Okay. So when current due to a battery passes through a coil, the coil creates its own magnetic field, and that changing magnetic field creates its own induced current. Okay, we just learned this. This is self-induction. And it's in the opposite direction to the change of current. Okay, so now we're going to define something called inductance. Remember, for resistors, we have resistance, right? For capacitors, we have capacitance. Now, for coils, they're also called inductors or coils, we have inductance. So what is it? It's basically the proportionality constant that tells us how much back EMF, how much back electromotive force, or how much induced EMF will be induced for a given rate of change in the current. Now, this part, if you look at this equation, this part was the Faraday's law. You learned this, right? Okay, Faraday's law. Now, we can rewrite it as, if I want to write it not instead of changing flux, but I'm going to write it as changing current. But if I do that, then there will be some constant in front of it, and that constant is called the inductance, the definition of inductance. Okay, so basically inductance is the proportionality constant between the induced EMF and the change in current. This also tells us that if there's no change in current, then the back EMF is not produced. So it only happens when the current is changing. And if you solve for now this equation, okay, let me show you. So now look at this equation. And from this equation, you can solve for L. So basically here, L will be, so delta T's cancel out. Okay, so L will be N. So it will be N times delta phi, which is the flux, divided by change in flux, divided by change in current. So basically, you can solve for L from this equation. Okay, let me give you an example. So let's say the inductance L of a coil is 2.9 millihenry. By the way, the SI units of inductance is Henry. Okay, so here in the circuit, L, the inductance of the coil is 2.9 millihenry. It carries a current 5.6 amperes. So the circuit is opened. Okay, so that means now it was closed. Now you open the circuit. What happens? This current, it falls down, right? When you open the circuit, the current decreases to 0 because you opened the circuit. Okay, and the current drops to 0 in time delta t. Okay, it takes some time for the current to drop to 0 because we have this coil here. So the coil basically makes it go slow. If there was no coil, then, and if you open the circuit, then the current would drop immediately. But because we have a coil now, or inductor, it makes the current go to 0 to have some time, take some time. So if during this process, the induced electromotive force is 7.3 volts, what is the time that the current drops to 0? Okay, what is delta t? Now, basically, what we are going to do is we are going to use this part of the equation and this part. Okay, so this is given to be 7.3. L is given to be 2.9. Okay, and so basically, the change in current. Now, what is the change in current? So the current initially is 5.6, and finally it's 0. It doesn't matter which way you write it because there's absolute value here. Okay. And if you solve this equation for delta t, then you can find the delta t to be 2.2 milliseconds. So basically the inductor here, the coil, it makes the current go to zero to take some time. I think by now you have figured out that the inductance is, or the coils or the inductors, they are trying to oppose what's happening in the region or in the circuit. So they have this opposing property all the time. Okay, so we learned these formulas in the previous slide. Okay, now there are some important points. First of all, induced EMF, it occurs when the current changes with time. Okay, if there's no current, then constant current means there's no induced EMF. The second point is induced EMF is in the opposite direction to the change in current. See, it's in the opposite direction to the change in current. Okay, so let's say if the current was to the right here and it was decreasing, so what this will try to do is it would try to increase the current in this direction. So the induced current would be in this to the right. So let me write induced. Okay, let me tell you again. So if I open the switch, okay, now it's not increasing with time. It's going to be decreasing with time. So now the current to the right is decreasing. The coil will try to increase the current to the right. Okay, so basically it's opposing change in current. Okay, not necessarily. So the induced current is not necessarily in the opposite direction. Okay, in fact, if you look at here, the induced current and the current in the wire, they are in the same direction. Okay, of course, the total current will be this plus this because they're in the same direction. You would basically add them up. So, for example, if the switch is opened and the battery is disconnected, the current on the coil, it's towards right here in this here. It's basically the current is to the right here. It will decrease, okay, because we opened the switch. So the back EMF will this time try to increase the current towards right because it was originally to the right and but decreasing. Now it will try to increase it to the right. So the coil acts like a battery. So now look at here. The coil acts as if, now I'm going to erase this, in this situation, to be able to create current to the right, induced current. So it's acting actually like a battery like this, plus and negative, right? So the coil itself is acting like a battery because if you have induced battery like this, it will create a current this way, which is the direction of the current. Of course, there's really no battery here. It's just acting like a battery. Okay, so what happens right after closing the switch? Well, basically, now let's say the circuit was open. Let's go in the opposite direction. Let's say initially it was open, so no current. And now you close the circuit. Okay, now you close the circuit. Now there's going to be current. Of course, initially it was zero, and the current will rise as the time moves on, and it's going to rise to a constant value. Okay, so the current increases and it reaches a constant value. Now, if you look at these formulas, probably you realize that they are actually the same formulas that govern the time dependence of the current in capacitors. And yes, they are pretty much the same formulas. So the maximum current is E divided by the voltage divided by R, right? The maximum current will be voltage divided by R. We think the resistance of the coil is zero. So it's an ideal coil. In reality, it's never zero, it's a coil. It will have some resistance, but here for ideal inductors, we will take it to be zero. So the only resistance here is the resistance in the connected to the wire. So now if you look at it here, at time equals 0, okay, this is 0. So e to the 0 is 1, okay, so this term is 1. 1 minus 1 is 0. So the whole thing at time equals 0 is 0, which makes sense. So time equals 0, you were at 0. What happens at time equals, let's say, a very long time? Okay. If very long time passes, then this is, let's take it to be infinite. Okay. So this is going to be 1 divided by exponential some infinite number. Okay. And this thing will be 0, 0. So it's going to be only this part then. So in, after enough time passes by, then the current becomes this maximum value, which is also shown here, epsilon divided by r. Now you may wonder, what is this tau here, this Greek letter tau? Well, again, if you remember from the capacitors, it is the time constant. For the capacitor, it was R times C. C is the capacitance in RC circuits, but here we have inductors, not capacitors, so it's going to be L divided by R, and L is the inductance of this inductor. So if tau is different, well, if L or R, if they are different, of course you get different taus. That means this curve may be like this, or it could be really fast like this. So if you want to control this curve, you would change either L, the inductance, or R in the circuit. Okay, one more thing about RL circuits. Okay, so if you have a circuit like this, let's say, again, you have a battery, you have the inductor here, and you have a bunch of resistors like this. So what should be this this R in the formulas that we used? Well, it will be not one of these, but the combination, all of them. So it's going to be, so you would calculate the R equivalent of this circuit here, and you can think of it as, so there is the inductor, and there's the battery here, and you can imagine this is connected to this equivalent current, equivalent uh, resistance here. And in the formulas above, you would use this equivalent resistance. Okay, so when the current reaches the maximum, so long after the switch is closed, so we close the switch, the current started rising, and it reaches some maximum value. So the self-inductance effect vanishes. Because if you look at here, now the current is not changing, right? And if you remember, the inductance was related to change in current, right? If the current is not changing after a long time passes, then the inductance effect would vanish. So the coil acts as a simple straight wire. So if you remember, so basically if you have an inductor, it's a coil, so after the current becomes constant, so basically this point, now it becomes basically a straight wire. So it does, because the current is now not changing, so there's no magnetic field lines produced. Well, there are magnetic field lines inside the coil, but they are not changing, so it's not going to create any back EMF or self-inductance, so it will act as if a straight wire. Now, I want you guys to compare this with the capacitors. If you remember, when the capacitor gets charged completely, it acted as a broken wire. Now, if you connect the capacitor to a circuit, now the current will pass through it as it charges, but when it's completely charged, the current stops, so it acts as a broken wire. Okay. Now look at these four circuits. So here, when I close the circuit, So initially there's going to be this effect, the self-inductance. There's going to be back EMF produced, but after some time, this is going to be, so the current will be maximum, and this will act as just a straight wire. Now the same thing will happen in the second circuit, but what happens if this acts as a straight wire? Then it actually short circuits the resistor here, right? So if there is a straight wire, the current will prefer to go through it instead of a resistor, right? So it's short circuited. So there is not going to be any current on this resistor. So all the current will go through this coil because it acts as a straight wire. Now what about the third one? I close the switch, and then after some time passes by, now this acts as a straight wire, and it will short this one, this resistor, and this resistor. So there will not be any current passing through them. Of course, there's going to be a current passing through this resistor. It's not shorted. But these two, this one and this one, they are short circuited. And on the fourth one, if I close again the circuit, then, well, this will, at some point, this will act as a straight wire, but it will not short any circuit because it will not short any resistors because these two resistors are parallel, it's connected to this one in series. So it shorts only the circuit elements that are connected in parallel, right? Here they're parallel. This one is parallel, but this one is in series, so it cannot short the ones that are in series. Okay, energy stored in magnetic field. So if you remember, let's make an analogy with capacitors again. The capacitors, they would store energy, right? They would store energy. How? Well, if you remember, let me draw it larger. There will be electric field lines inside, and so the capacitor, they would store energy in terms of electric field lines. Okay. What about the inductors? Well, inductors are coils, so there's no electric fields. Well, there are some induced electric fields, but basically the energy is stored in terms of magnetic field lines. Okay. And if you want to calculate the energy stored, it will be 1/2 L. L is basically, again, the inductance. It depends on the coil. So it depends on how large the coil is, what is the area. So it depends on the length of the coil, and times the current that passes through it. Well, it's actually squared. So this is the energy, magnetic energy stored in a coil. Now, if you remember the solenoids that I showed you in the previous lecture, they are basically coils like this. Now, I will not calculate it here. You can look at the book if you are interested, but the inductance of this solenoid is given by this formula. So mu0 is the permeability of the free space, so it's some number, okay, some number. N is the density of the lines, density of the loops. So it's basically uppercase N divided by length of the solenoid, okay. This is the length of the solenoid. And A is the area of the solenoid here, area of the loops, times length. Okay, so this is the inductance of a solenoid. Now, if you want to use it, so basically plug it here, L, so it will be 1/2 mu times N squared times AL. Now, so of course you have to plug what I is. Now, I'm going to leave it to you. Find I from the previous slides and plug it in, and ultimately derive this formula. So for a solenoid, you can write the energy like this. And if you want to find what is the energy per unit volume, so these uppercase U's, they give the total energy inside the solenoid. But if you ask me what is the energy in a given unit volume, then you would divided by the volume, and you can see that the volume is actually here. Area times length is the volume of anything like a cylinder. So solenoid is something like a cylinder. This is L, this is the area. If you multiply A times L, it will actually give you the volume. If you divide this by volume, so you will only get this part, which would give you the density of the energy. So it will give you not the total energy, but the energy density. Okay, now the transformers. So a transformer is used to change the voltage in an alternating current. So that means they are only used with AC current, not DC. Okay, so you cannot use a transformer with a battery. It should be AC current. So if you want to change the voltage or the current from one value to another, then you would use a transformer. Okay, so the changing B fields in primary coil. So basically what you have is you have some iron core, okay, and so here this is the primary circuit. This is the primary circuit, and this is the secondary circuit. Now, what happens is there is this AC source here, so it basically creates some current here, and that current is basically creating magnetic field lines moving to the right, to the left, or sorry, up or down here in this picture all the time. What happens if magnetic field lines are changing all the time? Well, the flux changes, right? So there's going to be some back EMF will be produced here, but that's not what we're interested in. What we're interested in is these magnetic field lines can be transferred to the other coil by this iron core. So this coil will feel those magnetic field lines that's produced by this coil, because those magnetic field lines will travel within the iron core to the second coil. So the purpose of this iron core here is really it's not really carrying the current. It's only guiding the magnetic field lines from the primary coil to the secondary coil. That's it. Really, there's no current flowing on this iron core. Okay, so changing magnetic fields in the primary coil, which is this one, are transferred to the secondary coil via iron core. So the flux in the secondary coil is changing. Why is it changing? Because magnetic field lines are changing all the time, because we have AC source here, which changes the current direction all the time. And this thing will induce the changing magnetic field lines here will induce electromotive force in the secondary coil. And so basically you can connect it to a light bulb and it would work. Okay, so by using different number of coils on both sides, we can step up or step down the voltage on the secondary coil. So basically what we can change here is the number of turns in this coil and the number of turns in this coil. And by changing these numbers, so it's basically NP primary coil number and NS secondary coil number. So by basically changing these, we can increase or decrease this voltage in the secondary coil. If you have the same number of N here, both, so if NP and NS, they're the same. Now let's look at here. If NP and NS, they're the same, you will get 1 here. So the voltages in the first primary coil and the voltage on the secondary coil will be the same, right? And the currents will be the same, right? But let's say if there are 20 loops here, but if there is 10 loops here in the secondary circuit, so NP divided by NS, this factor would be 2, okay? So the secondary coil the voltage in the secondary coil will be basically half of the voltage in the primary coil. So from here you can write Vp equals 2Vs. That means whatever the primary coil voltage here, the secondary coil voltage would be half of it. Or you can use 10 and 20, then it would increase the voltage by a factor of 2. And if you also look at these indices, so this is primary divided by secondary for voltages, but for the current, it's secondary divided by primary. So that means if you increase the voltage, okay, if the voltage is increasing, let me show you this way. Let's say if the voltage is increasing, then let's say voltage, then the current will be decreasing. Or if the voltage is decreasing, then the current would be increasing. Okay, so transformers don't work with direct constant current DC, so like battery, they don't work with that. Since the coils with direct current produces constant non-changing magnetic fields flux, which would not induce electromotive force in the secondary coil. So it will be just constant magnetic field, and you learn that constant flux doesn't produce any electromotive force or any current. So now again, look at the formula. Okay, so what we can change is basically the number of coils, number of turns in the coils, primary coil and secondary coil. And by changing these, we decide how the voltage in the primary, how the voltage will be in the secondary coil, or what will be the current in the secondary coil with respect to the first or the primary coil. Okay, so now note that if you double V, so let's say you have N, let's say N is 1 here and N is 2 here. Now, so this ratio would be 1 divided by 2. Okay, so that means if the primary voltage is, let's say 220, okay, then the secondary voltage here, it will be twice as large as 220, which is going to be 440. Okay, 440 if the primary is 220. And that's for the primary coil has only one loop and the secondary coil has two loops. Or it could be 120, it could be 100, 200, either way. Okay, now if you double the voltage, which we did here, so 220 to 440, now you have I, or vice versa. So this means the current becomes, it actually goes to half of the current in the primary circuit. So let's say if the current here in the primary, if it was 2 amperes, okay, 2 amperes originally here, let's say 2 amperes. Now if you look at the formula, if this is 2, if I primary is 2, then the secondary becomes 1. So then we get 1 ampere. See, the voltage increased by a factor of 2 from 220 to 440, but the current decreased by a factor of 2, which is the same factor, and it is determined by this ratio. So the power, if you think about the power, it's actually V times I, right? So V increased by a factor of 2, I decreased by a factor of 2, so the power didn't change. So the power here, P, in the primary coil and the power on the secondary coil, they are the same. That makes sense because you cannot create power, right, from out of nothing. So power or energy, remember power was energy divided by time. It's actually energy divided by time. Because energy is conserved, you really don't change power either. So the transformers don't increase or decrease power, okay? They can increase or decrease the current and the voltage, okay, but not the power. Okay, you may ask, okay, why do we need them? It's not really changing the power. Like, why would we want to change the voltage, for example? Well, one example that you use, the one device that you use every day, maybe a couple times, is the cell phone charger, right? So the cell phones, their battery work approximately 4 volts chargeable batteries, okay? But the outlet is it's 120 volts in the US. In the Europe, it's and rest of the world, it's 220. Okay, so it's a high voltage. So if you have high voltage on the wall, but if you need a much lower voltage, what you would do is you would use a transformer. Okay, so inside the charger, basically, there's a transformer. It reduces the voltage to approximately 4 volts. So it steps down the voltage from 120 or 220 to 4 volts. Okay, what about the zapper? So zappers are devices that are used outside, maybe in the balcony. So they are high voltage devices where the bugs or the flies come in and they are zapped, basically, they're burned. So zapper burns the flies. Why does it burn? Because it's a high voltage, 4,000 volts. How do you get 4,000 volts from the wall, which is 120 or 220 volts? Well, you can use transformer. It steps up the voltage, outlet voltage, from 120 or 220 to 4,000 volts. Okay. Of course, the current falls down, so the voltage goes up and the current goes down, but I'm not really interested in the current if I want to burn some flies. I'm interested in the high voltage to burn the flies. Okay, now the electron guns in the traditional TVs. Now, you guys are probably remember traditional TVs. They usually have an electric gun here, which shoots electrons to the screen, and they go all the way everywhere to produce the image. So these electron guns, they work with high voltage, okay, and approximately like 15,000 volts. Again, you would use a transformer to step up the voltage from the outlet to this desired voltage. Now, the other application is the power plants. So the power plants, they produce um, voltage of, it could be a dam, it could be a solar panel, sorry, not solar panels, a wind power. So they produce high voltage, but this voltage is um, so this is fine, but they also produce some current. So, but what you want to do is you want to minimize the current. So now transformers reduce currents by increasing the voltage up to 240,000. So it's almost like 20 volts. The reason that you increase the voltage is because you want to decrease the current. Now I'm going to show you, I'm going to tell you why you want to do that. Now here in the left figure, you see that this is the power plant, produces energy. And so you basically increase the voltage to decrease the current. Now, low current is required so that the electricity loss in the transfer through the wires is minimal. Now, if you remember the power dissipated from a wire, it could be an electric lamp, or it could be resistor, it could be any wire. If there's a current, there's going to be some heating, right, in the wire. So that power is given by this I squared current squared times R. So if you decrease the current, then you can see from the formula the power decreases, right? The power, the electrical energy goes into heat, which is wasted. It actually decreases if you decrease the current. And this is exactly why you increase the voltage. Because if you remember, if you increase the voltage, you actually decrease the current. So here the aim is to decrease the current so that less and less energy is wasted while we carry the electricity through the wires from one city to another. Okay. Now, when the electricity comes to the neighborhood, now in the neighborhood, you see these, again, transformers. What they do is, now this time, the transformers in the neighborhood, they step down the voltage. Remember, the voltage was initially about 240,000 volts. Now they step it down to 120 volts in the US, or in the rest of the world, they step it down to 220 volts. So let's look at these problems. Now we have this set up. Okay, the question is, what is the voltage across the light bulb? So you provide 120 volts here. What would be the voltage here? So we can look at the turns here. So there's the number of turns is here 2. The number of turns here is 4. So so the primary is 2 divided by the secondary is 4. Okay, so 1 to 2 ratio. So what happens to voltage? If primary is 120, if there's 1 to 2 ratio, then if you want to find this, so this is going to be, so if you write it, if you want to write it like this way, so this is going to be 1 over 2. So 120 divided by the secondary voltage equals 1 divided by 2. Now from Vs, you can find from here, it's 240. 240. So here the voltage is 240. Okay, now look at this part. This part is not a transformer, it's a connected wire. It's not a transformer. So whatever voltage here is going to be the same voltage here. Okay, so this is 240 as well. Okay, now this is stepping from 4 to 2. It's actually inverse of this one. So then it's going to go from 240 to, so basically half of it, 120. So the answer is 120. Okay, let's look at this one. Given that the intermediate current is 1 ampere, what is the current through the light bulb? If the current here is 1, what is the current here? Now, just look at here. Just look at the second transformer. So the voltage goes by a factor of 2. So the voltage goes by a factor of 2, right? That means the current will go up. The voltage went down by a factor of 2, so that means the current will go up by a factor of 2. So that means if there's 1 amperes here, then it's going to be 2 amperes here. Okay, so in this problem, it says there is a 6-volt battery is connected to one side of a transformer. Okay, and compared to the voltage drop across coil A, the voltage across coil B is, so here the voltage is 6 volts. The question is, what is the voltage here? Well, the answer is 0. The reason is because this is DC, this is direct current, it doesn't change. It's constant. Yes, it produces some magnetic field here, and those magnetic field lines are transferred here, yes, but those magnetic field lines are not changing, they are static. So if the flux is not changing, then you will not really produce any current here, so it will be 0. Okay, and that's all for this lecture.